So now we're going to look at that idea that integration actually is area under a curve. And the first 2-3 pages of our notes is going to go talk about the theory of why it works. On your exam, I'm not going to ask you to explain the theory of why it works, but I'm going to go through it right now so you can kind of get an idea of how this came about and why integration works for finding the area under the curve. Then we're going to go and do some examples with the definite integral. So just definition-wise, up till now we've been doing the indefinite integral. The definite integral is when you're looking between two specific points, and it will calculate the area under the curve. So here, if you wanted, in this sort of what looks like a sine or a cos graph, if you wanted to find the area between A and B, so the idea, so we're looking at this, we have two what looks like sine curves, and if you want to find the area between A and B, well, it's hard because those shapes aren't, it's not a smooth curve. But if you separate it into little rectangles like we have here in the yellow, it would be a good estimate. But right now, all of those rectangles, the way that I made it, are all below the curve. So if you added up all those yellow rectangles, you would get an area that's slightly smaller than the actual area. But if our rectangles were tinier, they'd be even closer to what we have before. And that's the idea. We're going to look at what happens if we make these rectangles, the length of these rectangles, smaller and smaller and smaller. In other words, making them thinner and thinner and thinner, then eventually our area will get really, really close to it. So if we look at one of those rectangles, what we can do is our yellow rectangle on the diagram before was this part, the part below. That was the yellow part of the rectangle. But we could look at two different rectangles and we could set up an inequality. We've got the yellow rectangle, which is obviously smaller than the area. And then we got the bigger rectangle going all the way to the top, which would be bigger than the area. So we'll set up some notation here. We're going to call the area of the entire shaded region, so that's everything here that's shaded, delta A. Then that area is between the rectangle with the height of y and the rectangle with the height of y plus the delta y there. So this area can be represented as an inequality. The small rectangle, length times width, is y delta x, and the bigger rectangle is y plus delta y times delta x. Now, if we divide both sides by that delta x, we get the following inequality. Now, this dA dx, or delta A delta x, that we've written it there, that's an average rate of change. But if we took the limit as that delta x goes to 0, can you see that this part here is just a derivative? So if we take that limit, because the definition of a derivative is taking the limit as that distance gets closer and closer to 0, well then that just becomes the derivative dA dx. Now, whoops, there we go. What happens is if we make this delta x, that get narrower and narrower and narrower. So first of all, we've seen that the middle part here becomes the derivative. But the other thing that's going to happen is that delta y that was at the top is also going to get smaller and smaller. Does it make sense that as this part here goes to 0 and gets smaller and smaller and smaller, then this part here, the delta y, would also get smaller and smaller and smaller and basically go to 0 as well. And eventually, when they get to 0, you've just got this thin line that's basically the same height as the function. So that means as delta x goes to 0, delta y will go to 0, and this becomes our derivative, which if we turn to the next part and simplify that, we've got that y is less than the derivative dA dx, which is less than y. Now when you get an inequality where there's a y on this side and a y on this side, and there's supposed to be something in between that, does it make sense that then it has to equal that? You can't have something in between two equal values. I've got a number in my head. It's bigger than 5 and less than 5. Wait a minute. It doesn't really work unless it's equal to 5. And that's the idea here. So once this inequality becomes in between these two, we basically can say that y is equal to the derivative. Now we have this equation that a derivative dA dx is equal to y if we integrate both sides. So if we take the integral of this side and the integral of this side, well, we've already know that integrating and taking the derivative cancel each other out. So if you integrate the derivative of the area dA dx, you're just going to get the area. And so now what this means is the area is going to equal the integral of our function. So here's the idea that says if you would like to find the area under a curve, all you need to do is take the integral of it, and you'll find that area. So now what we're going to look at now is that this equation, whenever you find it, it gives us the area from the origin up to any point. So if you wanted to find it between a and b, well, the integral, when you plug in b, will give you the area up to b. In other words, going back to here, when I do the integral and I plug in b, that gives me the area all the way back to the origin, up to b. So if I want to find the area in between a and b, I would then have to subtract the area up to a. And that would leave me with the area from b to a. So in order to do this, we're going to plug this into our equation. So we're going to set it up like this. This is called the definite integral. The definite integral has values on your integral sign. And it says you're going to find the area from a to b. So you integrate like normal, except now you don't have to worry about having the plus c. Because if you did one equation with a plus c, and you subtracted another equation that had the same plus c, those c's would cancel out, and so we don't even need to put them anymore. So with the definite integral, you don't have to worry about adding plus c. You've got a as your lower number, b as your higher number, even though you are allowed to set up an integral where the numbers are mixed up. It'll just give you a value that doesn't make much sense as far as area goes, but you could still calculate it. So what we're going to do, we're going to find the integral and not worry about the plus c. That's step one. We're going to write that result. Here, we'll do it with a really easy equation as we're going through. So we know how to do the integral of x squared. We're going to find the area between 1 and 3, just to watch it at the same time. What are we going to do for our notation? First of all, we're going to do the integral. The integral of x is x squared over 2. We're going to put that in square brackets and write 1 and 3 right beside it. So that's step number 2. Write your result, get your integral, and write it from 1 to 3. Then you're going to subtract the results. So if I plug in 3, I'm going to get 9 over 2. And if I plug in 1, I'm going to get 1 over 2. And when I subtract those, I get an area of 4. Graphically, we can see what this is because we chose such an easy function. y equals x is just this diagonal line through the origin. And we're trying to find the area right now between 1 and 3. So we're looking at trying to find that area. Now, if you didn't have calculus and you were trying to find this area in the past, probably what you would do is you would split this up into two different shapes that you know formulas for. You know that this is the point 3, 3, and this is the point 1, 1. So this rectangle has a length of 2 and a width of 1, so its area is going to be 2. And this triangle, because it's going from 1 to 3, has a height of 2 and a length of 2. So if you did base times height divided by 2, you'd get the area of the triangle to be 2. And you would add those up, and 2 plus 2 is 4, which is exactly the same result that we got from integrating. Now, this is one where we could use our old formulas to break things up. But if you had started with a parabola, then there is no formula that we have for area under the curve of a parabola. But the integration isn't that bad and not that hard to figure out. So this is what it looks like if you just use notation. What did we do? We figured out the integral and we wrote it from a to b, and then we just did f of b subtract f of a in the end to get the example, to get the answer. And it'll always be a numerical answer because we're finding an actual area.